This lecture is on mathematical morphology, so that is why I told you yesterday. You will understand better what is morphology. So it is a branch of the image processing part that considers the shapes that we are looking at the design. You will see which way we are considering shapes. Today we will see it with binary and tomorrow with place data. So yeah, so this mathematical morphology is a branch of the image processing that is nonlinear processing. It is based on sets. Yeah, so as this theory finite lattices that we will not see. Yeah, so the important part is A and sets. That those are the two keywords for this technique. And it can be used for many things. Let's see, image enhancement, segmentation, image restoration. So there are many tasks that can be solved by mathematical morphology. And then we will need to introduce a new notation for our case. And the first one is that we will define a couple of values. And we don't care if they are 0 and 1, 0 and infinite, 1 and 0, but they are just two values. And these two values, one is for the foreground, another one for the background, whatever values they are. And in the lecture, we will assume these two. So for the foreground, we'll assume 255 and 0 for the background. They can be whatever values. And so binary units take the values, and then you will define a couple of sets. So one is a foreground. The foreground of an image is all those pixels such that the pixel for the location is in the support of the image, and the image takes the value foreground in the for that pixel. So let's see. So let's say have an image. This is our object. We have here 200. 155. Here outside we have 0. So we will decompose this into two parts. First part is the foreground. The foreground. This will be a background. And so this set is defined as all the pixels such that all this plane is called the support of the image. So such that A belongs to the support. And it's a notation. That notation is the value. So it is this set. This set here is only left. And then all the rest would be the background. Okay, so this is the I call it B, F, G, and B, T without the 2. The notation stands 17. So F, G, so the foreground union the background is the whole image. There is no pixel that is shared by the foreground and the background. The background is the complement of the foreground. And the opposite. So the foreground is the complement of the background. With respect to the set I, so there is a whole set that is I, that is a set of all pixels, and then in that set, the complement of the foreground is the background. And so we are thinking of our images in terms of sets. And the interesting part of this mathematical morphology is just to make him think images in a different way. So for us, images so far they have been vectors. Okay, but it is not the only way of thinking of images. You can think of them as sets, or as what you are seeing is of course in Eagle. But you can also think them as functions, and you can differential equation in those functions. Okay, so let's say that this is our binary image. So this is our background, this is the foreground. I think pretty special. Yeah, the support of the image is the whole region where the image is defined. Yeah, actually, the support is defined where it takes the value formula. It is only the foreground. And then the complement of the support is the. Then we will define something that is called extraction element. So extraction element is kind of vector. So you can think of it as a vector. So it will have an origin, and then it will have some values that belong to the foreground, some values that belong to the background. So in our previous approach, for instance, in convolution, this will be value 1, this will be value 0. Now this is active, this is foreground, the rest is. And you can define the kernel the way you like. So you can define it this way, I think it's a way, it's a way, it's a way, it's a way. And define any kernel. And then we will, whenever we want to say that the kernel is 50 to the location, we will use this notation. This notation is another set. Set plus P is, let's say that this is my point P, my location P. I want to translate the kernel set the location. So what I have is to shift the origin of set, I have to shift it. And then for the rest of the kernel moves with the origin. So if I move the origin, I also the rest of the kernel. So this set plus B is another set, and it is another set that is also called the set neighborhood of B. Define it as a set. Okay, so let's say as the point P, this is a location. Then I do B plus set. This is a set. This is a point. So, and this operator here is takes a point from the left and a set from the right. Okay, so I have to define it. So this vector P plus set. So it will be another set. It is the set of all locations such that this location can be as E plus some delta R1, where delta long support of second. This is this. Okay, so it is simply saying, okay, I have this point here. I have moved my kernel here. So This is the delta R. The delta R is the difference between this point, the origin of the curve. So delta R is the support of Z. So it is where Z is different from 0. Then R, that is this point here. Okay. R, that is this R. This point here is the origin B plus something. But it is a set. So point plus set is set. A group of elements. Yeah, a group of elements. Okay, so then we can also define the reflection of a set. So but you have a structuring element set, and then you can reflect it. And the reflection is the set minus R minus C, where RC belongs to the support of set. So the reflection is another set. So and if you can note it this way, this reflection, you can also put it right in this one. And so for instance, let's say that you reflect this one. So this one is symmetric with respect to the origin. So the reflection of the game. But this one is not symmetric. So the reflection is just the reflection with respect to a point. This one is not symmetric. The reflection is the respect to a point. And reflection in 2 dimensions is the same as rotation by 180, but only 2 dimensions. So the general definition is this one. So it is reflection with respect to a point. And in 2 dimensions, it's the same as rotation. Okay, so now with this notation, let's introduce different operators. So the first operator will be dilation. Dilation is we have this input image and we want to produce this one. That is a dilated version of the original. So dilated means all the foreground pixels now they're wider. So for the foreground is now wider and is wider by this much. Okay. It's different difference here. Okay, so dilation is an operator. We will define this operator in this group. So I dilated by B is all the points in the support of I, the support of the image. So in the not in the support, the plane of the image, each plane, such that B plus the kernel reflecting intersection with the image is different from the null of the empty set. Okay, so let's see. So we have an image here. This is our foreground. This is our foreground. And now it is. Let's say that our kernel is that one. I shift the kernel to this location. Now, kernel intersection the foreground. Is it the empty set? It is. So this doesn't belong to the dilation. Okay, this doesn't belong to the dilation. What about this one? This one, kernel intersected with the foreground belongs to the, it only belongs to the dilation. This one belongs to the dilation. What about this one in the border? So this one in the border is here, and now there is an intersection. It's not a big intersection, but this region is intersected. So this one belongs to the intersection. And now you see how it is dilated. So If you are very far from the figure, your intersection will be empty. But if you are close enough to the figure, the intersection will be empty. And then you will extend these by a certain amount. How much? How much you will dilate depends on what is the size of your kernel. So this is one definition of the operation. It can be shown that it can be computed as the union for all the points in the support of E plus Z. So B plus Z was Z. Now we are gathering many sets into this union. And the same here. So it is can also be computed as you take all the points in the support of the kernel, and now what you see is the limit. Okay, so let's copy this. Let's copy this through. So what we have is I dilated, let's say, the union of the support. Okay. Be the support line of E plus second. It was one of the. Let's see the other. So the other is this one. This is a property rather than anything. When computing the like this, if you want. Support. Of that power. Okay, so I will write something that you are more familiar with. Okay, and I want to say I will take sum of all points of the Greek factor. I of R H of this is I of N. R W is for the outlets. R my and I will also write this. So this is the convolution that you are familiar with. Okay, so let's compare. So here, the image is moving, okay? And it is moving to the locations where H is different from 0. Because if it is 0, you don't care about those shapes, those locations, because you will multiply the image multiplied by 0. Okay, so let's look at this, and then you are summing. Okay, summing, gathering all those into a single image. Okay, so here, the image is also moving. It is moving to the locations where the kernel is different from 0. And you are also, so you are moving all those images, and then you are gathering all that information into a single image. So it has the same structure as the convolution. Only that now we are making it with sets. And here we have the same. So so now the kernel is moving. Here the kernel is moving. It is moving to the locations where the image is different from 0. If it is 0, it will be multiplied by 0, so we don't care. Here are moving to the locations where it's different from zero. And then you are gathering all those images. Gathering all those images. A single one. But it has the same structure. So dilation is a kind of convolution, but now defined with set. So this is a very interesting way of thinking, new way of thinking. Question? Okay, so yeah, so let's see how it works. Consider that we have this image. This is our kernel. Kernel is set A. Set A is this one. We have set A. And then we can, this is the result. So for all those pixels, the intersection, when you place the kernel in that location, you compute the intersection, the original, the intersection is different from the intersection. There is some intersection. So for instance, if you're in the middle of this thing, what happens at this point? So when I put the kernel in this, there is a hole there, but the intersection with set A is different from zero. It's different from the empty set. So that point will be free. So now we are dilating the foreground. So dilating the foreground with the shape. So dilation of these will close the holes. It will close these empty pixels, and then they will dilate also. This direction will extend a little bit wider. This direction. You can also feel this kind of so dilation is an operation that you do to close holes. Okay. So if this works as a convolution, one of the properties of the convolution we do is the following. So one of the properties is that delta on all things same. So does it behave the same here? So if I have delta dilated by kernel, is it the kernel? The answer is yes. So let's see why. Okay, so it is. You have to shift the reflected kernel to all the three locations, and then only keep those for which the intersection with the image is different from the image. Okay, so let's say this is our delta. This is the reflected kernel, and I shift it to there. So this point will not be kept because there, this point, there is no intersection. My shifted kernel, shifted and reflected kernel with the end of it. Of this point will not be kept. Okay, let's look for a point that is kept. So this point here is kept. Why? Because when I shift the reflected kernel to that location, the intersection with the image is different from zero. And the same for this one, same for this one. And you keep track of all the points for which the intersection is different from zero. This one is also different from zero. You shift the reflected kernel to this location, then the intersection with this one is different from zero, from empty. So this one you keep. Okay, this is the result. This is all the points for which if you shift the kernel, the reflected kernel to those locations, the intersection with the delta is different from it. So this is the dilation. Dilation of this delta with this kernel is the kernel. Again, that's the And so also of these two formulas, this one is faster to compute because typically the kernel is very small. So you simply have to move the image a few times and then compute the union of all those cells. This one is faster. Okay. Yeah.
Which is the best part.
Yeah, no, black, the gray.
Oh, yeah.
Are you missing? I will put you the same question, but now with convolution. I have an image, I convolve it with something, and I use information. No. With a convolution, you don't use. If it is a low pass filter, so every time you take an image and you transform it, you may lose or may not lose information. So it depends on what is the name of your kernel. If my kernel is a delta, I'm not losing anything. And don't forget something that in your image you have the ideal signal plus noise. So all these kernels and structuring elements, they are aimed to get rid of the noise. Highlight some figures. Okay, so yeah, this is another example of fitting the dilation through this image. So we are implementing this formula here. So you have a kernel, you shift the image to the location of the support of the kernel, and then you add all the elements. Okay, so let's say that this is our kernel, the colors here, so like pixels with colors. And then you shift, this is our kernel, you shift the input image, which is the to the location of the kernel. So this is the first shift. First shift is the central pixel goes there, and that's fine. Then next one is sorry, this is the one. This. Okay. So this one is the one that comes to the kernel. Okay, so what about, for instance, this purple pixel? The purple pixel is have to shift 2 pixels to the left, pixels to the top. So now you take your D, you shift it 2 pixels to the left, to the top. That is your shift in D, and then 2 pixels to the top. This one, and so we do 9 shifts. So these are our 9 shifts. Now we complete the union of all those shifts with the union pixel by pixel of all those shift in images. And this is what we get from here. Here are some more examples. So let's say this is our original image, and then we make the convolution of this dilation with this kernel, or this kernel, or this kernel, this kernel. And so this kernel is here. So we are making the convolution dilation. But the origin is here. So if the origin is there, we should expect that the whole image shifts to the half left. Then here the whole image shifts to the left. So we are, sorry, I said it. This is our kernel, and this is just a convolution with this delta, only this delta. You forget about the rest. This one is only the this delta. You forget about the rest. Then you complete the union of everything, and this is one. And for instance, you see this property that the delta result into the delta, so delta component with the kernel should be the partition. Be here the kernel. Okay. So let us introduce the erosion, and then after the break we will see. So the erosion is fancy, that this is the definition. So it is all the points in the image plane such that when you shift the kernel to that location, this set is fully included in the image. And there are two ways to compute that. One is this similar we did before. Now the gathering operator is not the unit, it is the intersection. And so it is the intersection of all the points belonging to the support of the image. And then you take D and the reflective set, so the reflective structuring element. You shift the structuring element in the location of B, and you compute the intersection of the or the intersection of all the points, the support of the reflecting kernel or image shifted to B. So that's this point. So I will write only one of them. I minus 7 of the intersection of all the these, the support, the reflecting learning, or D plus. So again, it has the same structure as that's the same structure as this one. If the image is only for the points where the kernel is different from children. In this case, it is not the kernel, but the vector. And then there is a gathering operator. In this case, the gathering operator is the intersection, it's not the union. So let's see an example. So let's say that this is our original. So, and the structuring element is select. Okay. So we have to keep only the pixels for which, when you shift the kernel to that location, the kernel is fully included. But let's say that we are in the middle here. The middle here, there is no problem. Middle here, when you shift the kernel, the kernel is fully included. Okay, let's see this point here. So, sorry, this point here. This point here, if I shift the kernel to this location, the kernel is not fully included. So I don't keep this one, and I don't keep this one. I don't keep this one. Neither of none of these points are kernel. What about this region? So this region, very few of them fully contain the kernel. So only this line at this point, when I shift the kernel to those locations, the kernel is fully included here. So this is called an erosion. Sorry, the foreground of the image is eroded. Now it is smaller because the kernel doesn't fully fit inside the image. Here you see the difference. So all these pixels in white, they are eroded. They are big. And you can see it as the foreground is eroding, but you can also see it as the background is expanding, it's dilating. That is another way of seeing it. So this point in the background is now dilated. Here, all these points in the background is dilated. The erosion, this formula that only moves the image is also faster. Any questions? Here we have an example of how this erosion, dilation, and the original relate. So here we have the erosion. So we have an original and erosion. And here we have original and dilation. Here we have the period. And there is some properties. That is, the original always contains the erosion. That's for sure. Also, the dilation always contains the original. And we will see more properties later. But these are the properties. So the complement of the image, so the background, dilated with the reflection, is the same as the image, the erosion of the image. Complement. So yes. So let's write it. So it is erosion, the complement of the erosion is a complement. I will write something and then complement of this. How is this called? This property of sets. This is a general property of sets. How is it called? Let's look. But this is one of the properties of sets. Let's look at it. So we have a couple of operators. Of two operators. One is the complement of the other. Or the complement of the complement, but kind of the opposite of the other. So here we have the same structure. Two of them, one is the opposite of the other. So if I want to compute the complement of one of them, it is the other one and the complement of the two elements. Okay, so this is the complement of this one. And this is not complement, but it's almost like a complement. So it behaves as the Morgan's laws. The same and the same here. See, the complement of these is the opposite operator. And the complement of the first one, the complement of the complement is the same. And this one reflecting. The reflection of the reflection is. Okay, so these are kind of Morgan laws, but now with dilations and all. It is no surprise that Morgan's laws appear somehow because this is a theory that is based on cells. Morgan's law is something that comes from cells. Okay, now we will introduce more operators. So these dilation and erosion, they are kind of very, very basic operators. We can enrich them. So for instance, let's say that we first do an erosion and then we dilate. That will be called an opening. So an opening, this is a new operator. It is defined in this way. So the opening by a kernel, by structuring element is I eroded by that and then dilated by that. And then we have the closing. Closing is the first dilation with the reflection and then erosion with the same. So let's see how these things work. So opening. So opening, we are first eroding and then dilating. So the erosion will remove all these parts and will make these parts very thin. And then we dilate the very thin parts. And then this is what we're covering. See? So we have the original, we erode the erosion is red here. So this is the erosion. And now we take the erosion and dilate it. This is our benefit. And now we can compare the opening with the original comparison. So the erosion is removing the isolated parts. This is isolated, so it is removed. And when you dilate, it's lost. And what about the very thick parts? Very thick parts. They are kept by the erosion, and then when you dilate them, they stay the same. So opening is a region, it's an operation that removes the isolated regions. This is isolated, this is isolated. And isolation with respect to this extraction element. So the extraction element, that is the shape that you're looking for, defines when something is isolated or not. And this is the same, but the three Ds are separated. So original, the ocean, and then the dilation of the ocean, that is the ocean. Yeah. Okay. Actually, this is an interesting topic. The opening of I by Z is the best approximation of I that can be made by taking union of translated copies of Z. Subject to the constraint that the opening is contained in the original. So one of these properties that we saw before, for instance, we saw this one, that the original always contains the erosion. Okay, so now we have the original always contains the erosion. So it always contains the opening. And this opening is the best approximation that we can do to the original is here, such that it is made of copies of set that are fully contained in the line. So it is the image that loses the least amount of information. And only loses these parts that are disconnected. This pixel is not disconnected, but it is disconnected from the point of view of Z, because Z cannot fit within that point. Okay, what about the closing? The closing is first dilated, then opening. So if we first dilate this C, we will fill this pixel here, and then we erode, and then we erode. So it will be, everything will be whiter. When you erode, make it thinner again, but now this pixel is bigger. Okay, so let's see. This is original, and then you dilate. So now you fill all these pixels. So these yellow pixels, they were empty at the beginning, but now because of the dilation, they become filled. And now you erode. So now it is this same thing of eroding or removing isolating parts, but not isolating parts of the background, not isolating parts of the background. At this point, and this kind of channel here, they were isolated in the background. So now they are removed. And when you erode, they are filled. And here are the same images, several images. So this is original, then you dilate, and then you. And all the points in the background that were isolated, they are isolated with respect to this this extraction. These are more Morgan laws. So we have seen this too. And now there are more Morgan laws, but now for the opening and the closing. So the opening and closing, they also behave as opposite operations. So the complement of the closing is the opening, And the complement of the opening is the closing. And you have to take care of the complements and reflections. There are no reflections in the expression. And here we have all the operations. So say that we take this image and we dilate, we enroll, open and close it with this structural element. Then this is the difference. Dilation. The foreground becomes bigger. Foreground becomes bigger with this shape. And this is the meaning of the word morphology. Morphology is attending to the shape of the structural element. It becomes bigger with the shape. Erosion, the background becomes bigger with the shape. Opening is erosion, then dilation. This is the opening. This is the closing, that is dilation and then the erosion. And then here is another example, dilation with the reflecting film. Okay, at the border, 0 is controlling. It's simplifying. Is there? And more, okay, so these are the basic operators. How can I use these operators to build anything useful? So, for instance, let's say that you give me this image and I want to know what is the boundary of this image. So, which pixels are in the boundary of it? And these pixels, so my definition of boundary would be an inside boundary. So the pixel belongs to the inside boundary. So when you look at this boundary, you can define the boundary outside or inside the object. So for us, it would be inside boundaries. And they will be 4 connected boundary. So 4 connected boundary is all the pixels in the boundary, they are connected by an edge. Okay. So let's say that we have this pixel, and this pixel is sharing an edge with this one, this one, this one. This is the 4 connecting neighbor. This section. Then we have the 8 connected ones. Have the 8 connected neighbor. The 8 connected neighborhood is the 4 connected neighborhood, but also this one. But they are sharing problems. And so 8 connected neighborhoods, they share edges and problems. And the 4 connected neighborhoods, they only share edges. Okay, so this boundary is an inside boundary that all the pixels in the boundary, they share an edge. Okay, so how is this calculated? Okay, so you take the original image, you erode by ZA. It's erode by square, ZA. So when you erode by ZA, this is the result. And now you compute the difference between the original and the erosion. And this is the result. Okay, so this result is inside the original image. It is a boundary. Only pixels in the boundary stay. It is 4 connected. Okay, so let's say that we instead of eroding with a set 8, we erode by set 4. Now we erode with set 4. This is the result. This is and this is the boundary. And now the boundary is an 8 connected inside boundary. So depending on which is the kernel that we use to load, you have an 8 connected inside boundary or 4 connected inside boundary. Let's say that I want the boundary from the outside. If I want the boundary from the outside, then what I do is the binary, and then so you have to originally dilate with the glass, so set form. You compute the difference with dilation minus original. This is the result. The result you see is outside. And it is an 8 connected outside boundary. And if instead of dilating with set 4, you dilate with the set 8. Now what you have is 4 connected outside boundary. So summary of this, you can compute boundaries. The boundaries are dilation, so dilation minus original or original minus erosion. And depending on which is the element that I use to do the erosion of the dilation, we have 4 connected or 8 connected boundaries. Yeah, so another problem. The 8 connected boundary, the 8 connected inside boundary is contain the 4 connected inside boundary. Yeah, you have a picture. Same for the outside boundary. Yes. Inside boundaries and outside boundaries are disjoint. Any practically simple properties. Okay, any questions about this section?
Paper states received everything down.
Which one? 38.
Why we everything down to the states.
Why this is 8 connected and this is 4 connected? So the 4 connected means that every pixel in the boundary, they share an edge with the nearby pixels. They share edges. The 4 connected means that they can share edges or corners. So for instance here, they're only connected by a corner. But in the 4 connected, they're connected by edges. No, igual no. Casi el mismo, pero no es exactamente el mismo. Mira, es como los cambios de una a la otra. Hay píxeles que aparecen, normal.
Cuando dice erosion by glass,
Glass is set for etcétera 4. La cruz. Este de aquí. Cuando hemos definido nuestro elemento, hemos dicho Z4 que es Z8. Entonces, la cruz que es de 4. ¿Alguna pregunta más? Okay, so then we move to the next topic, that is, let's say that I want to do the dilation of the sub-region. So I have this image. This is the region where I want to compute the dilation, and I don't want to compute the dilation anywhere else. So if I do the dilation as such of the original image, this is what I get. This with a cross. I know because this point that is isolated has become a cross. So you do dilation with cross of everything. This is what you get. Okay, but you don't want that. So what you do is you mask now. So you do the standard dilation. And now you compute the mask, you apply the mask on the region that you're in. And this is the mask that you And now you compute the union of the mass dilated union the original. And this is called the conditional dilated dilation with respect to mass. So you give me a mass, you give me a structural element, they follow this process. So first dilate, then apply a mass, then compute the union. That is the result. This is called conditional dilation with respect to energy. And I can use these to label objects. So let's say that you have in your image, you have a couple of objects, and you want to count. The computer wants to count. How many objects you have in the sequence. So what you see is that you have many pixels to zero. Some of the pixels are set to 55. So let's say, and you don't know how many objects you have. So let's say that you take one pixel that is 255, and you say, okay, it will be object one. So you have object one, and now you do this conditional dilation. So conditional dilation of this one is this one. And then all the points, this is dilated, and all the points in the region that are in the conditional dilation, they get the same label. So this started being object one, but now these two other pixels that are nearby, they also get the label one. And now label one has this mass, and now you do the same conditional dilation, and you get the pixels that are in the conditional dilation, get the same label. So now these two other pixels, they will get the same label. And now you do again conditional dilation. At the end, you have fully labeled this object. So if you do conditional dilation again, you don't get any other experiments. So this object is finished. And now you do the same with the next object. So you look for another object that has not been labeled. Let's say it is this one, and you do the same conditional dilation. You assign the same label. Now conditional dilation again, same label. So now you would realize you have a couple of objects here. So conditional dilation is an operation that helps you count how many objects you have. And we can make more fancy operations. So let's say that you have a binary image that's been corrupted by noise, and you want to restore it. So you want to reconstruct and remove the noise from this binary image to get this one. So how can we do it? Okay, so these points, they are isolated points in the background of them, so isolated foreground points. So these isolated, we know that the opening gets rid of them. But the opening, you see, removes the points, but also has removed some interesting parts of the underlying signal. So we want to recover it. So how to do that? We can follow this. So let's say that you first do an opening. Do an opening, it's going to be here. Now, this is just to. Okay, so now I take a copy of the current image. And now you do dilation with plus or square. Now you compute the intersection, so this intersection between the original and the dilated one. If the image is different from, so if the image, these two operations have changed their image, then you repeat. And you repeat this process until the image doesn't change anymore. So the process is first you open, then you dilate, you complete the intersection, and then dilate, complete the intersection, dilate, complete the intersection, until it doesn't change. And then this is what we have. This is the result. You start with this, and then dilate, compute intersection. Dilate again, compute intersection. Then at the end, you can recover pieces of the underlying signal and get rid of the noise. Okay, more. So let's say that you want to compute the skeleton of an image. Let's say that given this image, you want to compute the skeleton. This is the skeleton that we want to compute. There's some nice pictures on. Sorry. So you can see what we want. So we have this picture here. We want the skeleton. We have to picture. We want the skeleton. Picture. This is the skeleton. We want to compute this skeleton. Okay, so how to do that? So will be defined in this way. So the skeleton is the union of an operator that is the skeleton with radius r. Okay, so it is the union from all the possible radii of this skeleton with radius r. And this skeleton of radius r is the set of all centers of maximal disks of radius r. We will see what that means. So let's see. So the red points, they are maximal disks, and the blue points, they are non-maximal disks. Let's see. Okay, so let's say that I look at this point. This point is of radius 1. So we have drawn a disk of radius 1. And in this disk of radius 1, it is not maximal. Why? Because I can construct a disk of radius 2. This red point is disk of radius 2 that fully contains the disk of radius 1. You see? Okay, so this point, this blue point, is not the maximal disk. This red point is a maximal disk of radius 2. If I cannot find any disk of radius 3 that fully contains the disk of radius 2, and it is inside the image. It goes outside the image. Same here. So this is not maximal because I can find one that is bigger and that fully contains the other one. Okay, one thing, why this is a square? So this these things. So you have a point. Let's say that we construct the disk of values R. So all this content is in that disk. You say that R belongs to this disk. This that is centered, say that this point is R0. Radius R. Why? Why is that? So why a point belongs to that great at least? Because the distance from R was 0 is smaller than equal to R. And if your definition of distance, if you do 2 points, It's this one. Thanks. Why? This is our definition of distance. Then the this is, well, what if my distance is defined in this way? My distance. The distance. Defined in this way. It's the maximum of Alex inside. But this is another distance. And now the this, so the this is about this is. And again, trying to look at the structures. So what do we have? What is the structure of this? This is, you have to compute something for the individual components. Individual components. And then you have to gather them. Only that the gathering is not equal. So I think that the best part of this lecture is that it makes you think of many things that you think for granted in a different way. So what is an image? Now images are set. What is a convolution? And this convolution we have to define for the dilation. What is the distance? Kind of stuff. Okay, so these are not maximal, these the red ones the maximum. We can plot all the points where we can find maximal disks. So this maximal disk is the raw skeleton. But this raw skeleton, it has isolated points, and you don't like these isolated points. And it is not thin. So see if they can move it. Okay, so we have the original. And how to compute the skeleton. So we will do something. That is, we will erode with a kernel that is sedate. And this sedate will have radius 0, radius 1, radius 2, 3. So this is with radius 0, so it doesn't change. With radius 1, radius 2, and radius 3. And if we continue, we don't have any other pixels, so we stop there. Okay, so now we do the opening of this one. Okay, so we do the opening with this, with radius 1. So this is the opening of this one. This is the opening of this with radius 1, opening, opening, and opening. And now we collect everything. So now we collect everything. That is, yeah. So what is the difference? Okay, so you have to complete the difference. It's two differences here. Okay, the differences here. This is the difference of this and the difference of that. Now you collect all those a single step. Okay, so the process is first the erode. Then you compute the opening of this, and then you compute the difference, and you collect all these differences. Yeah, so now, if this is the raw skeleton, there are isolated points. So you delete them. So you delete all the connected components with less than 3 pixels. And how do I do that? I have the operation. This operation helps you to identify connected components. This will tell you this is a connected component, this is another connected component. So we remove all the connected components. With less than 3 pixels. Okay, this is for this reference. Now you dilate. Now you do. This is the dilation effect. Now you compute the intersection of all the dilated components. So this is the dilation of this one, the dilation of this one. Now you compute the intersection of all those. You add all those intersections to the original skeleton. So this was the raw skeleton, this was the full skeleton, because after removing the small pieces. Then you computed these connecting points with this intersection. And then you add the connecting points, the skeleton. After this one, you add the connection points. Now everything becomes connected. But with these, you can do this kind of stuff. You apply this. So for instance, here, it is very typically done. So you have this set of vessels here. You complete the skeleton. And what is the connectivity between those vessels, for instance? So this is a point where it branches. Like binary. Any question?